All right, for the second lecture this week, we're going to talk about coastal environments here. And just to sort of give you a brief overview of some of the features that you might expect to have an influence on the sedimentary deposits that you would find along the coast and what those might look like if you're dealing with certain types of coastal situations. So we can kind of start off by making a little bit of a brief classification, if you will, that typically the non-deltaic coastal environments are going to be dominated by three different processes. And now these may be all present at any particular location, but at least at some location at some time, one or so of these processes will be the most dominant. Now, that can vary through space and time as a coast evolves or as a storm occurs and so forth. But these environments in particular that we'll talk about are these wave environments, right? And you can see, kind of as we talked about with deltas as well before, the impingement of waves upon the coastline can direct sediment, can result in ripples and so forth in ways that can really shape the coast and deposit sediment in a way that gets preserved as stratigraphy. So we'll talk about wave coastal environments. We'll talk about tidal environments and a little bit about what features you might expect to see in that might indicate that you're in a tidal environment. And then we'll also talk a little bit about storm depositional environments as well. Okay. You can see in this tidal environment, one of the key features that you might pick up on here is you have this sort of ebb and flood tidal deltas on both sides of your barrier island as you go into the estuary. So you get sort of almost a deltaic or a bar-like deposit on both sides, indicating that the sediment transport is at some point dominated in the outward direction and in the inward direction, depositing sediment on both sides. That's one of the features that you can see here. One of the features you see in the storm-dominated environment is these overwash deposits. So as if a storm occurs, you can breach the storm surge can result in a breach of the dunes that are protecting the back barrier marsh here, right? And you can get these overwash deposits that flow into the marsh and deposit a bunch of sand back there. And that's a typical indicator of a large storm event. These were taken, don't remember which storm I took this from last year after the hurricanes that we saw last year. I believe, but this is a Gulf Coast image. So in wave-dominated environments, we have sort of a typical scheme that looks like this, where you have sort of a foreshore environment here that is exposed to the open water, right? So this is the foreshore. That might include the beach here, or that would include the beach, that would be included in the beach, I should say. The back shore being the component that is less frequently visited by waves. The foreshore is relatively constantly inundated by waves in this case. Then you might have dunes, right? A ridge of dunes that forms along the shore, along the coast, that kind of protects the lagoon or the marsh that might be behind there. And in a storm situation, you might get washovers and with a lagoon behind there. But typically, when we're talking about wave-dominated environments, we're going to be interested in this sort of region here, where we're going to look at the beach, the upper shore face, and the lower shore face, and those two are sort of defined by their position relative to sort of the waves and the tides that are dominated on those locations. So this is a typical beach profile through a sort of let me go back one slide. So we'll talk a little bit about this shore face environment. We'll talk a little bit about the exposed environment here as well. So this next figure is just the exposed component of the environment. And you'll see that, again, you'll get shore face deposits that are predominantly exposed but wave derived, so you'll get actually bed forms that'll form as a function of more wave driven flow. So as a wave hits the beach, you get flow that recedes backwards, so you might get unidirectional bed forms, you might get plain bed and so forth. Those are relatively common features on the near shore environment. Then you'll get dunes potentially in the back shore, which will have aeolian transport processes and so forth, right? As you get further offshore into this sort of upper shore face environment where you have regular interaction with waves, one of the sedimentary features that will become important is the influence of the waves themselves, right? So waves can be, waves are these periodic features on the water surface, if you will, that have a height, they have an amplitude, they have a wavelength, and the water above the sediment surface has some depth. And what you might be interested in maybe thinking about is, if you're looking at a stratigraphic deposit, where along the spectrum of wave sizes or wave periods or something like that you might be interested in. And one of the features that we can look at will be wave ripples that get generated. The waves can have a relatively wide variability depending on the location and how they impinge upon the bed. Typical values for ocean waves, though, sort of range in the order of a couple of meters. Coastal waves might be a little bit lower than that. Sort of the largest waves that have ever been recorded, the largest significant wave height ever recorded is like 19 meters. And the sort of highest, largest wave ever recorded those are unreliable estimates in the 30s of meters. And these waves are moving at some speed, right? Which the combination of the wave amplitude, the wave length, and the wave celerity are what result in the stresses being acted upon the bed that would result in movement of sediment and the creation of ripples, right? And so one thing to think about when you're thinking about how waves interact with the bed to create bed forms and move sediment is the fact that typically a parcel of water in a wave situation moves in a circular orbit. Now this will change a little bit as the wave impinges upon the bed, right? If the wave impinges upon the bed, that orbit will flatten, okay? So you can see that illustrated here with our lovely little seagull that's just cruising around on this wave. If you were to track that seagull, if it were staying just floating and not kicking its legs, it would go in this nice circle. And the same is true for parcels of water in the flow itself. And those circles or orbits decrease as you go closer towards the bed. When they start to impinge upon the bed, then you can imagine you have a fluid velocity in this direction followed by a fluid velocity in this direction that's going to transport sediment one way, and then it's going to transport that sediment the other direction when the wave passes. And so what that results in are what we refer to as oscillatory ripples. If you look at the velocity field here, you can see as the wave progresses, so these are slices of time following tracer particles in the flow, images of sediment in this case. You can see that the wave is moving and the velocity is from right to left in this case, and the sediment and the fluid is being sheared in this direction. You can see there's little vortices that are forming in the separation zone here, right? And then when the wave crest passes over, let me see if I'm going to get this right. Yeah, so the flow is generated in the backward direction as you're coming towards the crest, right? So that first image is this part of the wave. Then as you get towards the crest, the the velocities sort of stagnate. Sediment might settle out a little bit when that happens. And then as you go towards the trough, the velocity field reverses and you get flow separation on the backside here, like that, right? And then that process repeats itself over and over again. And you end up in a situation where you get sort of a symmetric transport of sediment in one direction, the next direction, back, forth, and you build up these bed forms which are symmetric in their profile, right? And we call those oscillatory ripples or symmetric ripples or wave ripples oftentimes, okay? And so that's a very common feature on the bed in wave transporting environments in the near shore and the sort of shallow offshore environments, anywhere where the wave is able to impinge on the bed, okay? So that's going to be a common occurrence in a lot of these systems. Another thing that waves cause, and we talked a lot about this when we talked about deltas, is that wave refraction. If a wave impinges upon the shore in a not perfectly perpendicular direction to the shoreline, but meet it at an angle, then the wave will start to slow down, right, while the rest of the wave travels faster, and so it can kind of refract around a point, right? And these refracted waves, as they impinge upon the shoreline, can result in the development of a current as the sort of one side of the wave reaches the shoreline first and slows down, right? Then the rest of that wave can continue on a little bit faster than the first part. And so the fluid velocity on average then ends up towards the direction of the refraction here, if that makes sense. So as the wave is coming in this direction, the average flow velocity then and the average sediment transport is going to be in this direction, and it's going to cause what's called a longshore current, right? And longshore currents, in conjunction with the swash and backwash of wave on sediments, can result in what is called longshore drift of sediment, right? So if you have, in this case, the waves are impinging in this direction, right? This is from the Texas Gulf Coast here. As the waves impinge upon the shoreline here, and you get swash and backwash and swash and backwash, that sediment over time is going to be pushed in one direction along the coastline, right? So a sediment grain might be, as the wave comes in, be pushed downshore a little bit, and then as the wave goes out, it'll be pushed downshore again, and so on and so on. And so the individual sediment grains will over time, transport in the direction of that longshore current, if that makes sense. Okay, and you end up with features like this. This is now an engineered coastline, and you can see there are jetties or little wing dikes or something that are revetments or whatever that are put in here to protect the beach, so that these nice houses still have nice white sandy beaches. And you can see there's this sort of piling up of sediment on one side, right? And those are almost kind of like little bed forms, if you will, looking at it in that direction, right? And that's indicative of the fact that the longshore current is predominantly moving in this direction. Another cool thing that you can't quite see it in this image, but if you look really closely, you can kind of see there are bed forms that are organized not necessarily perpendicular, but sort of in the direction of this longshore current, and those are bed forms that are formed by this current component that might have a wave and current component to those bed forms. So we call those combined flow bed forms that result from this combined wave and unidirectional current aspect, right? So this can form in longshore current environments. It can form when there are other marine currents present. It can form in environments where there's waves and tidal currents going on. But unlike the previous image or particle trajectory or fluid parcel trajectory that I showed you, if there's a combined current, right, a fluid parcel will make those loops, but those loops will be kind of smeared out such that that fluid parcel will end up moving downwards, downstream, or down current over time, right? And so as that impinges upon the bed, you get these weird combined flow bed forms that are common in these sediment transporting environments that especially have things like longshore currents and so forth. And so these are often what you might see, where you see asymmetric bed forms with ripples on top of them, right? Superimposed bed forms that reflect both the unidirectional nature and the oscillatory nature of the current. Okay. And I'll say that it doesn't take a lot of current to generate a asymmetry to these combined flow bed forms. And it may only take a tiny amount of, in this case here, it's 1/6, right? The current velocity is 10 centimeters a second, 0.1 meters per second here. Whereas the reversing current velocity, the peak velocity driven by the waves, is 0.6 meters per second, or 60 centimeters per second. So you can see in this case, it doesn't take a lot of current to generate an asymmetry to these bed forms. Okay, so this is a relatively common feature to see in wave and longshore current and current dominated environments. So all that to say, those are some of the features you might expect to see, or some of the processes that can drive the generation of the different types of bed forms. And so you can start to think about, well, where would those processes be impinging on the bed, driving sediment transport, and therefore what types of sedimentary structures you might expect to see deposited in the stratigraphy, depending where you are on your beach profile. So this is sort of the standard beach profile diagram that includes the terms that you might expect to see based on what types of waves might be present. So if you get further out onto the shelf, you tend to be more likely to be in purely oscillatory wave environments, because the waves are not impinging upon the coastline at an angle at this point, and so the longshore drift component is not resulting in a current that drives asymmetric waves or asymmetric bed forms to form. So if you're in this offshore environment on the outer or inner shelf, you might be more likely to see purely oscillatory waves, where, depending on your depth, you have storm waves that are just depositional, or storm waves that can be impinging on the bed in such a way that you also get erosion, right? And so in this case, you would see those as, say, fine laminated sands with purely constructive wave ripples, right? If you get it a little bit shallower, the large storm waves that would create the oscillatory flow might also be capable of scouring the bed. If they're big enough and the flow is or the water is shallow enough, you can get what are called hummocky cross stratification, or hummocky bedded sands, where the storm waves are able to erode and deposit sediment. And I'll show you some images of those, right? As you get more into the translational component of waves, right, where the waves are building up, breaking, and forming surf as you get closer towards the nearshore environment here, right? So in the shore face environment, you go from lower to upper shore face as you get closer towards the sort of exposed beach, right? And so these, by the way, are defined in the context of wave base here, right? So normal wave base, an average everyday wave, the base at which those can reach, the velocity field from those waves can reach the bed, defines where you change from the near shore to the shelf environment, right? So this transition occurs at normal wave base, right? So an average everyday wave can no longer force sediment transport on the bed below that depth, and so that's where we would define the break between the shelf and the nearshore environment. This is mean lower low water here, right? This is mean low water. So mean lower low water has to do with the lowest low tides versus just the daily low tide, right? So this would have to do with your spring versus neap tide situation. The mean low water of a daily tidal cycle would determine where you reach the top of your shore face environment, right? So on an average day, this would become exposed due to tides, right? And this is mean high water, right? And this is the storm wave limit, where you go from the beach to the coast is where the storm waves no longer are impacting, okay? And so in this near shore face environment, right, you're more likely to result in a wave situation that also has some combined current influence, and so you're more likely to get cross-bedded sands, trough cross-bedded sands that indicate that you have a unidirectional component to your wave here. So that's relatively common in the shore face condition. When you get up onto the beach, because you have very thin flows, right, as a wave breaks up onto the beach and then swashes back and so forth, because the flow depth is so small and the velocity is so high, you end up in a high Froude number condition and are more likely to be plane bedded, upper plane bed sands for any of the said structures there. That's not entirely true, but oftentimes is the case that this is more likely to be what you would see. And you would see coarser, potentially better sorted sands in the beach as you're winnowing away fine material. Does that make sense to everybody? So what some of these structures might look like is, for example, in a near shore face sediment, you might have asymmetrical bed forms. There might be some pebble lags or some gravel lags that are relatively well graded, but you likely see these cross-bedded, trough cross-bedded sands resulting from those asymmetric wave impingement scenarios here, right? And so that's a relatively common feature to see in a nearshore environment. And ultimately what these different sediment transport environments might look like for a wave-dominated coastline is if you had, say, a prograding coastal system, right? The coast is moving outwards. You're going to get a coarsening upwards where you're going to move from the lower, burrowed sands, less wave impingement in the lower shore face to the upper shore face where you have these cross-bedded sands into the foreshore where you have planar but offshore dipping strata, and then as you move upwards, you get more into the Aeolian dune component of that, right? The opposite might be true if you're in a transgressive system where it's stepping backwards, right? And you start out in a lagoonal environment. Maybe you have tidal deltas or tidal flats and washovers in the marsh area. So this might be, say, and then ultimately towards the backshore dune, and then you would repeat this succession over again, right, in the opposite direction. Does that make sense? So this would be if the sea level were reversing in the opposite direction, but you can see both cases you're coarsening upwards. Okay, so it's important to think about more than just the coarsening or fining trends of the sequence, but actually what's going on in the sediment itself. So what the structures look like, and maybe what the burrowing and bioturbation and so forth look like. And we'll talk a little bit more about the lagoonal and tidal components in a minute. As you go to more storm-dominated environments, some things that you might expect to see on these systems is you might get what are called tempestites or storm deposits, where, say, in some of your more finer grain material, you get pulses of sand, and those might be hummocky cross-stratified sands where a storm makes landfall, and you push a bunch of coarser material out into the sort of shelf mud deposits, and so those would be referred to as tempestites, where there are these hummocky or rippled sands sort of surrounded by shelf muds. That's a relatively common thing to see, where only the larger storm events can hit the coast, erode a bunch of sand off of the beaches, and transport it further offshore. That's relatively common to see in a storm transported environment. And then as you go up more into the tidal or shore face conditions, you might expect to see, if you get further inland, you might expect to see things like overwash deposits and so forth. Like, for example, here on this set of imagery following Hurricane Sandy, right? This yellow arrow in all of these images is the same location. I think this date is not correct. Yeah. Oh no, this is correct. Okay, sorry. These are two different locations. So this location and this location are before and after Hurricane Sandy, right? And you can see that these individual houses are being pointed to. And in this case, right, both of these situations resulted in an overwash fan here, right, that has deposited a bunch of coarse sediment, sand, into the lagoon behind. And you would see that preserved in the stratigraphic record as a coarse, sandy, deltaic looking deposit in this muddy lagoonal system in both of these cases. Okay, so that's one way that you might identify a storm, either a storm dominated or a storm influenced environment like this. Okay. Another thing you might expect to see, and I talked a little bit about this, is hummocky cross stratification. So if you're below the normal wave base here, you're off on the inner shelf, right? In this region where the storm waves are capable of impinging upon the bed, and they are capable of having enough sediment transporting power, enough shear stress that they can actually cause some erosion, you get these really cool cross stratification features formed. And they generally tend to be very large wavelength, low angle cross bedding, where they erode the bed in these very low angle truncations, right? And so you end up with bedding that is cutting across each other at fairly low angle junctions like this, right? You can see that the erosional feature here cuts this bedding at a fairly low angle. Same here, right? And that's a characteristic component of hummocky cross stratification. And here's what that might look like in an outcrop, right? You can see that there's a little bit of steepness to it there, but generally speaking, they're relatively shallow, what we would call hummocks and swales, right? So the swales are the lows, the hummocks are the highs, right? Here's a hummock and a swale here with relatively low angle truncations, although with some exceptions depending on how oblique you are. Here's another great image of that. Here, again, you can see that unlike fluvial bed forms where the truncations might be at 30 degrees or 25 degrees, these are at, only a few to maybe 10 degrees truncations, right? And then you can see another one here, right? So this would be a swale truncating in a previous hummock, and so on and so forth. Okay. Here's another great example of that. Again, you can see very, very broad sort of swales, hummocks, right, and so forth. And so you can start to build out an understanding of what might be potential event beds based on some of these outcrops, where, say, in a normal situation on a continental shelf, you might have, general sedimentation occurring, fine grain deposition, relatively low sedimentation rates, so burrowing can occur and critters can be crawling around and feeding on the bed. So you would get these burrowed, maybe finer sands and muds here that might be separated by an erosional interval, say when the storm first occurs. Then you get the hummocky cross stratification, the amalgamated bedding, so to speak, which may then be followed again by a burrow zone that might burrow into that hummocky cross stratification and burrow into sort of the slower sedimentation, shelf sedimentation. And that process may repeat itself over and over again in some cases. And this would be sort of a, storm event beds stacked on top of each other that would tell you that you're probably below fair weather or normal wave base, but above the storm wave base. So that tells you where you are on the inner shelf environment. Does that make sense? So this is fantastic hummocky cross stratification here, by the way. You see those low angle truncations. That indicates that it was a erosive waves, right? Because you could truncate those beds, but you're not getting steep lee angles and steep cross stratification. It's very gentle because they're large waves with very long wavelengths, but they're tens of meters above you in depth. Okay, so that's enough for waves for now. The other influence on coastal systems that we haven't talked about is tides, and so tides result from the both lunar and solar positions relative to Earth, and result in the alternating sort of a positive or a negative sea level in your location over the course of a day as a function of the gravitational pull of the sun and the moon. And in our case, the moon is the primary driver of this. Okay, the moon is much closer, even though it's smaller, and so its gravitational pull is much larger, pulling the oceans in sort of in line with the lunar position. And so the moon produces two tidal bulges, right, in sort of on axis with itself here, in a sense. And so the seawater will move up into a slight bulge relative to the moon's position, and this can be modulated by the position relative to the sun. So we can have what are called spring tides when the moon is either in line with or opposed to, or during the full and the new moon of the sun here, right? And so when those two gravitational pulls are acting in the same plane, you get the high tides and the low tides. Alternative to that, you can get what are called neap tides, and the neap tides occur in the first quarter and third quarter when the moon's gravitational pull is perpendicular to the direction of the sun. And so this results in dampened tidal modulation or tidal heights, right? So you get low tides, high tides in those conditions. Okay, and in some cases, this can result in the switching between a daily versus a diurnal tidal cycle, where sometimes you might get a tidal cycle in some of these neap tidal systems where the twice daily component kind of fades away, if you will. And so what this might look like in some given system, and you can look at this for any tide gauge system anywhere on Earth, you can see what the high tides and the low tides look like over the course of a sequence of tides. So 60 tides would be about 30 days in this case, right? And you can see the sorry. So you can see the spring tides and the neap tides here shown when you're in a full moon versus a new moon, right? In those situations, right? So in the full moon phase, when the sun and the moon are opposed to one another, that's when you get higher high tides and the lower low tides, if that makes sense. Okay. And so certain regions have a mixture of diurnal versus semidiurnal tides, and that can change depending on where you are on the world's coasts. And this is a useful thing to think about when you start thinking about looking at sedimentary structures, because sometimes you can see the record of changing tides in the stratigraphy based on the sediment transport changes in a particular location, and you might be able to tease out whether you're dealing with a diurnal, a semidiurnal, or a mixed tidal sequence. And so again, a diurnal tide refers to a situation in which you have one high tide and one low tide per day, essentially. So systems like here in the northern Gulf of Mexico, we're more likely to have a situation like this. These are sort of more microtidal regions, right, where you only end up with one cycle per day. And now here in the northern Gulf, that can vary depending on whether you're in a spring or neap tidal system cycle. Then there's the semi-diurnal. So these are half days, right, where you have 2 high and 2 low tidal cycles per day, right? So on the Atlantic coast and a lot of other regions where you have more exposed coastline, you end up with these semi-diurnal tides. So these are all in red. This is the more, I would say, the norm for most situations. And then you can also have situations where, depending on the circumstance and the position relative to the direction that the tidal impingement occurs, those are relatively complicated reasons behind this. But you can end up in a mixed tidal system where the high water, low water, then the next high water and the next low water would be significantly different in heights. This is often the case in parts of the Gulf of Mexico and the Caribbean exhibit this. California and the western coast of the U.S. exhibit this as well. These are pretty common, I would say, as well. And sometimes you see this here on the Gulf Coast, where you're like kind of in a semi-diurnal cycle, but one is very dominant. Okay. And these tidal flows can result in really interesting sediment transporting phenomena, as the tide can result in transport in the coast, in the onshore and the offshore directions. So here's an example of a tidal inlet where it's broken through a barrier here into a lagoon or an estuary, and you have a flood and ebb tidal delta. So on both sides of this tidal inlet, you have sediment transporting in some parts of the day in towards the estuary, and some parts of the day offshore, and you get a little delta forming on both sides, right? So this is relatively common in a tidal dominated environment. Okay. You can also see the influence of tides in tidal channels in river systems in these estuaries, where you can see that during the ebb current, the flow is significantly downstream, and then during the flood current, the flow is significantly upstream, and you get these bidirectional bars where they seem to have like slip faces or flow that is routed in both directions down these bars. And that's a relatively common thing to see as well in these tidal channels. Okay. And that would manifest itself in potentially seeing bar forms in the stratigraphic record that have that have components that dip in both directions. Okay. And so what some of these sedimentary structures might look like are what we would end up calling either bidirectional or rhythmic bedding, depending on the system. So here's some examples of rhythmic bedding that you might expect to see in a tidal situation. So these are what are called tidal bundles from the this is the Cretaceous in Utah, Curtis Formation. And as you get a dominant current stage or tide, either current or tide direction, right, you get the foresets that dip in sort of typically in the offshore direction, right, and then during the subordinate or this the current direction going in the opposite sense, you get a reactivation of that previous plane. You're reworking some of the sediment that was deposited at the front here and then depositing it again on a sort of back slope dipping sedimentary structure. So you might get cross bedding in both directions in this case. You may also get mud drapes that appear as the current slackens, right? So as you get towards the inflections in those tides, the current will slow down as you're transitioning from an ebb tide to a flood tide or a flood tide to an ebb tide. Okay, and so that's what you see here. You see this is the dominant direction of the current, and then you get a fine-grained mud deposit on the tops of each of these. And then if you were to look carefully, it's hard to see in the imagery here, behind here you kind of get these interesting cross beds that might form in the back stepping direction. And I've actually posted a Sketchfab three-dimensional model of this tidal bundle sequence. This is not my photograph, this is from another lecturer, but I compiled several photos into a 3D model that I took years ago out there as well. So that's one way that you can get tidal bundles here. And so each of these would be considered one tidal bundle, if that makes sense, right? You can also get cross stratification in detail that forms due to tidal influence at a smaller scale. And in this case, you can get it in a couple of different ways depending on the relative strengths of the ebb tide and flood tide at that particular location. In this first scenario, you end up with cross bedding that's pointing down in one direction and then cross bedding that's pointing back in the other direction, and that's referred to as herringbone cross stratification, okay, where it's reversing directions, and you get cross beds that are sort of opposed in their directions. If the tidal magnitude in the upstream direction is maybe not necessarily enough to on the flood tidal direction to actually transport sediment in, and it can be either depending on which side, say, of a ebb tidal or flood tidal delta you're on, whether you're dominating one direction or the other. You may only get mud drapes that deposit on the slip faces of these cross beds. You may not always get herringbone type cross stratification. Although in this case you can see that there's some of both in this, right? So there's herringbone here, and then there's another larger scale bed form maybe that's forming here that's only getting mud drapes on it. You may even see small herringbone on the face of those to indicate that in one direction there were only small ripples forming on the face of the large ripple here, the large dune. And then reactivation surfaces are, as we mentioned, those surfaces where if you had a cross set here and then it was maybe eroded and the sediment was removed and deposited in the reversing tide, and then another bed form started to migrate out in front of that, and then that was maybe eroded back a little bit. Those are referred to as reactivation surfaces, and those can be telling of tidal sequences as well. So here's some great examples of this. This is from Arkansas, a photo that I took. You can see in this case that there's tidal cross stratification that's going in both directions. Down here there are mud drapes. Here's some great mud drapes forming some couplets here, and so forth. Okay. Here's some herringbone cross stratification from Colorado. Again, you can see that the reversing direction of tides is playing an influence here. And then finally, the last little bit that you might also expect to see are something called rhythmites. And these are little packages of sediment that form primarily from suspension settle out or plain bed sedimentation, and you can see that they're the grain size is changing systematically, but also you're getting an expansion and contraction of the bed thickness as a function of some potential cyclicity here. And that cyclicity is something that I actually want you to look at in today's assignment, or this week's homework assignment. So I've posted a Sketchfab 3D model of this as well. You can take either the snapshot from here or a snapshot of your own from the Sketchfab model. And what I want you to do is to go through and trace the individual bedding horizons, right? So here's a layer, here's a layer, here's a layer, right? So pick, the bedding horizons that you want to see or measure and trace out those surfaces. Count the bedding. It'll help to trace it out so that you can see the thickening and thinning cycle a little bit better. Count the number of beds in a thick to thin cycle or a thin to thick cycle, and see if you can make an interpretation and see what it might guide you to believe about what the sort of thickening and then thinning of that bedding represents. So I'm going to post the Moodle link with an assignment box, and you'll have a short answer section in Moodle, and then there will be a place for you to upload a PDF or a JPEG of your annotated image to show me what you think. Okay, so I want you to spend a little bit of time, not too much, just kind of thinking about how what that thickening and thinning might represent, and counting those beds and making some interpretations based off of that. All right. So when we return next week, then we'll move down slope or down basin into our deep water environments. All righty.